In this section, I'd really like to focus on just gaining an understanding as to what exactly a limit is, and kind of get a sneak preview as to why we care about this thing called a limit so much. We're going to spend a whole chapter, about 25% of our class, just talking about this thing called a limit. Why do we care about it so much? Why is it so important? Well, it turns out we use this to build other cool calculus stuff. So we're going to give kind of a little sneak preview to this. We'll come back and talk about that more in depth once we get to chapter 3. But for now, we're going to start with hopefully a familiar definition right here. It says the average velocity is the change in distance divided by the change in time. So if you have a position function s of t, and you want to find the average velocity over a particular interval, it's s of b minus s of a over b minus a. This should hopefully look really familiar. Perhaps you saw it in college algebra, or you saw it in a physics class, or you just saw it in some science class that you took in the past. But if not, here, this is going to be a pretty important formula here in this section. So let's work with this in example 1. We're just going to practice using it. So we have this position function s of t equals negative 4.9 t squared plus 30t plus 20. We're just going to practice applying this formula. We're going to find the average velocity over each of the following intervals here. So the first interval I have here is 0 to 3. So this might be like, okay, if I'm driving a car, perhaps maybe I just threw an object up in the air, right? If I throw this object up in the air, what is its average velocity from 0 seconds to 3 seconds later? And if I apply this formula here, I might say, okay, well, I'd like to end up with s of 3 minus s of 0 divided by 3 minus 0. But I think before we get into that, it would probably be helpful if first we looked at what is s of 3 first and what is s of 0 first. And for these two, we're just going to take those and plug those into our position function up here for t. So for s of 3, we're going to plug 3 in for t. Negative 4.9 times 3 squared plus 30 times 3 plus 20. So we can go and crunch those numbers. We should end up with 65.9. And then we'll do the same thing with 0 here. I've got negative 4.9 times 0 squared plus 30 times 0 plus 20. Here, this one's a lot nicer to work with here. We'll just end up with 20. So now we can take these two, plug those into our average velocity formula over here. S of 3, that's 65.9 minus S of 0, that's 20, divided by 3 minus 0, that should just be 3. So I should end up with 45.9 divided by 3 would give me 15.3. Is that right? Let me just double check. I don't trust my arithmetic here. Yep, 15.3. Now we're talking about a velocity here, right? And I didn't give a unit, so let's suppose that we live in a world where we use the metric system and everything makes sense. So 15.3, we'll say meters per second here. And that's all there is to it. So this really wasn't there's really no calculus involved in this problem. It's just kind of applying this formula that maybe we've seen in the past. But maybe I change my mind. Maybe I say, okay, well, you know what? I don't want to know the average velocity from 0 to 3 seconds. Maybe I want to go from 0 to 1 second. So let me do this in a different color. I'm just applying that same formula here. So I'm going to start with s of 1 minus s of 0 all over 1 minus 0. And again, we might just off to the side, we might want to look at, well, what's s of 1 and what is s of 0? And in this case, s of 0, we actually found that before. That's just 20. So we don't need to do that work again. But s of 1, we'll take that, we'll plug that into our position function. Negative 4.9 times 1 squared plus 30 times 1 plus 20. Here we'll crank those numbers out. We should end up with 45.1 here. And okay, now we can take these numbers and plug these in. So I have 45.1 minus s of 0, that's again 20, over 1 minus 0, this is simply just 1. So let's see, 25.1 over 1, which is 25.1 meters per second. So we could keep doing this, and we could change. Let's suppose I want to keep 0 the same, and let's say maybe I'm very indecisive, and I just keep changing my mind as to what that second number, what that right-hand number should be. I just can't make up my mind. It's really tedious to have to take that second number, plug it into your position function, and then find the average velocity. So what I'd like to do is in this next section, I'm going to show you how we can generalize it here. So now I'm going to say from 0 to h, where h is just some real number. So if I wanted to go from 0 to 0.5, I would just take 0.5 and plug that in for h. So let's see here. Let me change my color. Again, I know I want to use that average velocity formula, so I would like to use s of h minus s of 0 all over h minus 0. But maybe you say, boy, I don't know what s of h is, so let's go and find that. Let's see what that is. S of h, so we're just plugging that in for t, negative 4.9 times h squared plus 30h plus 20. And normally at this point we'd go and do some calculations here, but there's not really any calculations to do. I can't simplify this. There's no like terms. There's not actually anything I can do. So we're just going to leave it, and we're going to take that number, plug it in. S of 0, we know we've done that a whole bunch. We've seen that. It's 20. So s of h here, s of h, that's going to be negative 4.9 h squared plus 30h plus 20 minus s of 0, we've said that is 20, all over h minus 0. I know that that's just going to be h. So let's look at our numerator here, and we can simplify this a little bit. It works out really nicely. I've got 20 minus 20. Those two are going to cancel each other out. So let's see. I've got negative 4.9 h squared plus 30h divided by h. And I look at that numerator, I say, well, there's a greatest common factor of h. Let's see if we can simplify this a little bit more. So if I factor out an h, that'll leave me with negative 4.9h plus 30 all over h. These two cancel, and I'm just left with negative 4.9h plus 30. And this kind of simplifies the whole process of finding the average velocity now. So if I went back to that first problem, I could get the exact same result. Let's say I wanted to work on that same problem, and that same problem is part A, 0 to 3. So here in this case, what I'm really saying is h is equal to 3. So I could take that number, plug that in for h. So negative 4.9 times 3 plus 30, I would get exactly the same thing, which, let me just double check, yep, 15.3. So I can just choose whatever number I want for h, and it simplifies this process a great deal. So I'm going to use this now in this next part right here. But before I jump into that, I want to make one more connection here. Hopefully when you looked at this formula up here, this average velocity formula, hopefully that kind of rung some bells elsewhere too. That actually is another pretty famous formula from college algebra. That is actually just the slope. It's just the slope formula. If you want to find the slope, really, right, if I'm working with s of b minus s of a over b minus a, I can think about this as y2 minus y1 over x2 minus x1. This is essentially just the slope formula. So don't overthink it. We're just talking about slope here, and we're talking about in particular slope of the secant line here. So what I mean by slope of the secant line is, if I go back, let's just talk about part A here for a moment here. In part A, we were working on this interval 0 to 3 right here. So I've taken my position function and I've graphed it. And really what I did in that first part, in part A, I said, okay, here is 0. Here is 3. I essentially just said, you know what, I found, oops, let's see, I was hoping that would be a straight line. I found the slope of that blue line right there. We've said that the slope of this blue line is equal to, what did we say, 15.3 here. And then in the second case, okay, we said 0 to 1. In that case, maybe we'll do that in green here. We said from 0 to 1. In this case, we said our slope was roughly something along those lines. I know it's not perfect, but in this case, we said, okay, this time our slope of the secant line was 25.1. So I want to see what happens. What happens if I keep taking this point over here? 0 has stayed the same always, but it's that second number that I'm kind of thinking about changing. What happens if I take that number and I move it really close to 0? What happens? I'm really, really interested to see. So here, one definition I'm going to give you right here, the instantaneous velocity is the velocity of an object moving at a particular moment in time, right? So if you drive 120 miles in 2 hours, you could say, okay, well, I drove 120 divided by 2, that's about an average of 60 miles an hour. But that doesn't necessarily mean that you were always driving 60 miles an hour. At some points you might have been driving 65, at some points you might have been driving 55. It just depends on what moment in time you're talking about. So that's the difference between average velocity and instantaneous velocity. So I'm going to use s of t from example 1 and actually our result from part C to find the average velocity over these following intervals. So I could say, okay, let's take s of 0.1 minus s of 0 all over 0.1 minus 0. And sure, I could go and take that number, plug it in, but we did all of this work in part C, and let me go back and get that here. In part C, we said negative 4.9 h plus 30. So I'm going to just take 0.1, since that's my h here, and plug that in for h. So negative 4.9 plus 30. Oops. Negative 4.9 times h, which is 0.1, plus 30. And we can go and we can calculate that out. Let's see, I should end up with 29.51 here. So, okay, that's cool. But maybe I want to get a little bit closer, right? I want to get as close as I can here. So maybe I say, okay, 0.01. So here, s of 0.01 minus s of 0 all over 0.01 minus 0. Remember, this guy right here, I'm really working with 0, comma h. So in this case, h is really 0.01. So here in this case, I can say, well, okay, let's just take 0.01 and plug that in for h into that formula we found back in part C. Negative 4.9 times 0.01 plus 30 here, and in this case I'll end up with 29.951. Okay, well, maybe I want to try and move even closer. Maybe I say, okay, 0.001. No, 0.01, not close enough. We want to try and get a little bit closer here. So again, I'm thinking about 0, comma h right here. So h is just 0.001. And again, I'm just plugging that into that formula we found in part C. So I'm even just going to say negative 4.9 times 0.001 plus 30 here. And in this case, I should end up with 29.995, I believe 9951 here. My calculator actually just cut it off. It only rounded to 3 decimals, but my guess is there's a 1 there at the end. And we can keep doing this. We can keep playing this game, going closer and closer and closer, right, just by adding a 0. So the next logical step, you might say, okay, well, maybe I want to work with 0 to 0.0001. And I can always move just a little bit closer and a little bit closer and a little bit closer to 0. But that's not where I want to go with this question, or excuse me, I guess that is where I want to go with this question here. Part D says use parts A through D to estimate the instantaneous velocity when t equals 0. So notice that these intervals here are getting smaller and smaller and smaller every single time, right? I'm getting closer and closer and closer to 0. So these average velocities should be getting close to this instantaneous velocity, right? If I'm making my interval very, very, very small, I'm starting to talk about one particular instant in time, one particular moment in time. So I want to ask myself, well, what are these average velocities getting closer and closer and closer to? Well, 29.51, 29.951, 29.9951. It looks to me like they're getting closer and closer to 30 meters per second. And if you're not sure, maybe you need to go and you need to try another interval. Maybe you try 0.001 just to convince yourself. You can add as many zeros as you want, just to convince yourself, just to see you're just going to keep getting closer and closer and closer to 30. So this thing that I want to talk about here, it says as we make our intervals smaller and smaller, approaching some number. So we're getting closer and closer to 0 here. The average velocity will approach a unique number, which is called the instantaneous velocity. This single number is called a limit. And this is how I want you to think about limits. I want you to think about limits as, okay, what are we getting closer and closer and closer to? It may not even necessarily be what the value of the function is, as we'll see in the next section here, but I want you to be thinking about limits, and the question you should be asking yourself is, what value are we getting closer and closer and closer and closer to?